Hello, my name is Seth Russell. This work was co-developed with Peter DeWitt. We are both with the Department of Biomedical Informatics at the University of Colorado Anschutz Medical Campus. I'll be talking today about healthcare data harmonization using Shiny, clinical expertise, and relational database management systems. The alternate title of my presentation is Data Harmonization, the unsung hero of everyday data science projects. There are many others who have contributed to this work. Although my name and Peter's names are on the slides, this work would not be possible without the effort and guidance of many other people. Before I begin, I have a few disclosures. This work was grant funded from the NIH with Drs. Tel Bennett and Nelson Sanchez Pinto as principal investigators. This presentation is related to the work the group and I am part of have published previously. Two of the major publications are shown here that came out in January of 2024. Additionally, this work was based on protected health information. The Colorado Institutional Review Board has granted us a waiver of consent for this study. Other regulatory approvals were sought and obtained for individual U.S. and non-U.S. sites. Our motivation for this project was to study sepsis, which is an infection with life-threatening organ dysfunction. Our work focused on pediatric sepsis. Many pediatric survivors of sepsis have ongoing physical, cognitive, emotional, and psychological sequelae, which may have long-term effects on them and their families. Sepsis in children has important differences to adult sepsis, including age-specific variability of vital signs, developmental age-dependent immune function, pediatric-specific comorbidities, epidemiology, and outcomes. Sepsis is a leading cause of death among children worldwide. Prior to this work, the most current pediatric-specific criteria for sepsis were published in 2005 based on expert opinion. In 2016, the third international consensus definition for sepsis and septic shock, known as sepsis 3, defined sepsis as life-threatening organ dysfunction caused by a dysregulated host response to infection, but it excluded children. In summary, pediatric sepsis criteria needed to be updated. Our aims in this study were to 1. Determine the optimal clinical criteria for each pediatric organ dysfunction in differently resourced settings and care environments. 2. Develop and validate novel pediatric sepsis criteria. 3. Design, build, and evaluate prototype CDS tools to facilitate use of the new pediatric sepsis criteria. The data harmonization process I'm talking about today supported these aims, but was not described in detail in our previous publications. For this study, we had data from many sites across the United States and around the world. Total encounters was approximately 3.6 million. Also in the graph in the upper right is a comparison for the recent adult work improving the adult specific sepsis criteria. That work had about 1.3 million encounters. This slide represents the data used as input for data analysis and machine learning. For the most part, sites were asked to provide data following this schema. Text descriptions were provided of each table and column to each site. Discussion was had with each site to answer questions about what was needed to verify sites could provide the requested data in the format we desired. Despite this requested format and specification documents, there are many variables that differed greatly across sites due to electronic health record differences, practices of clinical care, language differences, and other factors. In reality, what we had was a rainbow of data input from each site. Some sites were very close to the desired schema, others were not close. We had approximately 2.2 billion rows of data as input. After harmonization, we were left with approximately 1.7 billion rows, so 500 million rows of data were not needed. This disconnect between the provided and desired schema is commonly referred to as the square peg in a round hole problem. Quite a bit of work needs to be done to get what was provided to meet the needs of the project. Others were the closely related round peg in a square hole problem, or not everything that was needed had been provided. We made it work, but there were some gaps around the corners. Data harmonization is the work that makes the connecting lines. This is often overlooked in many projects and left out of publications, but is very important. Just a few lines seem so simple in a diagram, but it took significant effort over several years to implement. Key technologies involved were our SQL relational database management system. We used Google BigQuery and R Shiny. Other tools involved include Microsoft Excel to view and edit CSV files, GNU Make to control our build processes, GNU Parallel for job control and multiprocessing, and Python and Bash. One of the goals of the harmonization process was to have clinical experts to be able to do as much of the mapping as possible. To that end, we created a collection of mapping files, CSV files, that allowed those with the proper knowledge to easily identify which rows are of interest and which are not. Initial mapping started with string-based searches performed by the data science and statistician teams. In general, the common labs we worked with have similar names around the world, though some language translation is needed. Luckily, in our case, non-English language clinical data was mostly translated for us already, but we also had clinical folks fluent in multiple languages to help with the rest. This is a small sample of the laboratory mappings needed. While standardized ontologies and terminologies do exist for laboratory results, such as the logical observation identifiers, names, and codes, also known as LOINC, due to poor adoption of standardized terminologies at individual sites, the effort to first map to LOINC and then to our desired schema was deemed to add little value. Instead, we mapped what we needed and only what we needed. Total rows for test mapping across 10 sites is about 4,000. We had similar mappings for vitals, medications, and other source data. Note that the mapping rules included both inclusion rules, as highlighted here in green, and exclusion rules, highlighted here in red. These rows allowed us to identify rows of interest that should be used in the final analysis and machine learning pipelines. Some labs, such as bacterial cultures, needed to come from a specific specimen type. This is an example of a CSV file generated that physicians reviewed to evaluate lab results based on specimen and the possible text values and numeric minimum, maximum, mean, median, standard deviation, and quartiles. Most culture tests have string responses that we primarily categorized as culture taken or not, though we did some additional curation depending on the site, looking for specific bacteria present. Other lab tests are generally numeric only, though there are always a few rows that have strings such as unable to calculate, or less than or more than some threshold value that is based on the limitations of the test being performed. In order to preserve as much data as possible, some generic rules were applied to labs at the limits of tests. Some code we used is shown here. Greater than x was converted to 1.1 times the numeric value. Less than x was converted to 0.9 times the numeric value. As this study covered 10 years and 10 sites, some unit harmonization also needed to be performed. In many cases, we have the source unit and can apply a known conversion factor to get units how we want, as shown here for a few of the laboratory tests. Not all were as simple as this. In some cases, the source data had no unit provided. Body temperature was often sent over as unitless. Based on review of the data and clinical input, we came up with numeric thresholds for determining source unit. After the previous harmonization configuration, we found that we still had values that were not realistic, meaning not compatible with life. For many labs, vitals, observations, we also gathered minimum and maximum values. Items outside these ranges were set to null. This file is available on the public repo of the papers as shown here. Additionally, clinicians would review frequency of specific labs across sites. While we might not know beforehand exactly how many of a specific test is being done at a site, looking at general ratios of tests gave us a good idea if we needed to look for missing mappings or reach out to a site for more guidance. The final mappings are available at our public GitHub repository as referenced already. Once the harmonization files were created, they were loaded as tables in the database. This sequel shows how some standardized mappings, which were generic and applied to all sites, were combined with site-specific mappings. The not exist clause around line 26 allows for site-specific mapping to override the generic mappings. As I've only a few minutes to cover this, you can view the source code at the link on the slides to review in more detail later. The harmonization process is then performed in multiple phases by data type. The first phase of the lab test harmonization process pulls in all the rows of interest and apply the unit conversion and string to value conversion, as I've talked about earlier. The second phase was to remove all those rows meeting the exclusion criteria, as shown previously. Several other phases exist but are not shown here. Additional phases perform value mapping for string values and dropping values outside reasonable ranges. Once done, some of the summary files helpful for mapping shown previously are generated, and the data is copied to the production location where analysis, statistical analysis, and machine learning occur. This multi-phase process allowed for debugging, review, and validation. Once the CSV files were created and processed, a significant review process is needed. We use Shiny for this important phase. In this example, one can see the lactate labs across sites. My purpose here isn't to teach you how to use Shiny, but to show what value Shiny and similar tools can provide. The key benefit here is self-service exploration of the harmonization process result. Although all project personnel have access to the underlying relational database, having a standardized method of viewing the information as both a table and a visualization were very helpful for developers and clinicians. We found this combination of box and whisker with violin plots helped both quick and detailed review to validate mappings. Full details are shown below in table format, so values can be sorted and filtered based on a number of different aspects of the labs. Additionally, one last detail that may be of interest: some of the source data tables were very large. Loading all the data into memory required significant resources, more than 128 gigabytes of RAM, so we often work with samples of the data, random 50% for more thorough investigations, 10% samples for quicker spot checking. Clinicians and data scientists could look at labs by name and site. If a problem was found here, updates to the mapping CSV files were made and the harmonization process was rerun. Unit review is important as well. Some labs are fairly standardized across sites around the world. Other labs have many units and ranges in common usage, which can be very problematic when building statistical models, performing machine learning, and creating clinical guidelines. Additionally, some sites had changes in the same lab over time. One unit may go out of favor or be retired or added over the approximately 10-year period covered. Due to the flexibility of Shiny, other filters and visualizations are also possible and easy to do. We created similar visualizations for observations, events, vitals, and medications. So this concludes my presentation on how we harmonized some 2 billion rows of input data. We used a combination of expert input and some cool technologies such as R-Shiny, and thus we were able to solve our data harmonization problems. Hopefully you can use these same patterns to create your own song and achieve the success you seek in your own projects. My slides are available at this GitHub repo. Please reach out to me with any questions.